Welcome back to Physics 371 Online. I want this to be kind of a fun topic that we cover today because it's not covered in any great detail in the book, and yet it shows that some very simple models in simple mathematics can give us some quantitative insight into the behavior of both paramagnetic and ferromagnetic materials. So what we're first going to do along the way to describing a quantitative model for ferromagnetism is first analyze the thermal behavior of a collection of magnetic dipoles that don't interact strongly with one another in the presence of a magnetic field. So the magnetic field would tend to align these dipoles, except that there will be a competition because of the temperature of the system. The higher the temperature, the less well aligned these magnetic dipoles will be, even in the presence of a magnetic field. And we'll use the very simple model of a two-state system that I'll describe in just a minute. This will give us a simple model for paramagnetism. Then we'll follow what was done historically for the first time about 100 years ago that was the basis for the first real understanding of ferromagnetic materials as arising from some type of interaction between magnetic dipoles. And we'll use a theory that's very useful in statistical physics that's called mean field theory. So our assumption at the beginning is that we have a system of n magnetic dipoles, and you can think of these as simply being located on the atoms in a sample. And each of these has an identical dipole moment m. In the presence of an external B field, quantum mechanics tells us that there's only two possible energy states. And this is the origin of what's called the two-state spin system. The magnetic dipole can either line up with the magnetic field or against it. Now, classical physics would say that there would be a whole continuum of alignments and that they would each have different potential energies. But in quantum mechanics, there's only two possible alignments. And we can see how this works schematically. If we have a B field in a diagram pointing upward, the magnetic potential energy of a dipole in the presence of the B field, we've seen this before, it's minus m dot B, and that means, according to quantum mechanics, two possibilities. We can either have the magnetic dipole lined up with the applied field, and that will of course be the lowest energy possible, or we can have it opposite to the applied field, that'll be the highest energy, and zero potential energy is in the middle, of course, where there's no magnetic field at all. So statistical mechanics tells us that at a particular temperature T, there's a probability for each of these states to be occupied. And the probability is proportional to what's called a Boltzmann factor, which is an exponential to the power of minus the energy over kT. And the way we write this down, we say that the probability for a state with energy U to be occupied is equal to some constant times e to the minus u over kT. And of course, you will recognize Boltzmann's constant. You've seen it before, perhaps in a chemistry course and maybe in introductory physics. Here it plays an important role in defining this probability. So this allows us, in a very simple way, to find an expression for the thermal average magnetization of this n-dipole system. The reason that there's a temperature dependence, again, is that at very low temperatures, we would expect that the dipoles would line up very, very closely with the applied field, whereas at higher and higher temperatures, they would tend to have more randomized orientations and would align less well with the applied field. So let's see how that works. Therefore, the probability for a particular dipole to be aligned with the field would be the constant A times e to the mb over kT, right? Remember, it's e to the minus the energy, and the energy was negative mb. So it's minus and negative or positive. Now this means that if there are n dipoles, the number aligned with the field would be equal to n times this probability, right? And the same kind of thing holds true in reverse. There's a probability for an individual dipole to be lined up against the field, and therefore we can say that on average the number of dipoles aligned anti-parallel to the field would be the total number of dipoles times this probability. Right? And we can go back to the definition of magnetization as the magnetic dipole moment per unit volume and realize that that's simply going to be the difference between the number of dipoles lined up with the field and the number of dipoles against the field. If they were equal to each other, then the magnetization would be zero, because you'd have cancellation of dipoles lined up with the field and against. But when there's an excess, right, then the term in parentheses times the individual dipole moment divided by the volume gives you the magnetization. And it's easy to calculate. We just take these two expressions for n up and n down, or n parallel and n anti-parallel, and substitute them in, and we'll factor out an A, and we'll see that what's left is this difference between two exponential terms, which apart from a factor of 2 is a hyperbolic sine function. And the argument has in it m times b, which is this characteristic energy associated with a magnetic dipole in a magnetic field, divided by kT, which also has units of energy and can be regarded as a measure of the thermal energy of the system. So that's the magnetization, but we still have this constant A in here, and we'd actually like to get rid of it. So the way to get rid of it is to realize, through a very simple normalization argument, that n up plus n down has to equal the total number of dipoles, or, in other words, the sum of the two probabilities for any particular dipole has to be 1. So we make that substitution, plug in for P up and P down, and we find out that that's 2a times the hyperbolic cosine of this argument that we've seen above. Now we can solve for a, because 2a times this hyperbolic cosine is just equal to 1. So this tells us that a has this rather unusual looking form, but we're going to plug that into the expression for the magnetization. And so what that's going to give us is actually a hyperbolic sine divided by a hyperbolic cosine. So we get that the magnetization as a function of temperature is a term out here in front. Oh, and by the way, I made a mistake here. I see this 2 should have canceled out, right? Because there was A had 1 over 2, and then M had a 2 in it. So there is no 2 in this expression. But what we see then is, apart from the 2, what you've got out in front of the hyperbolic tangent function is what's called the saturation magnetization. And so we define it as m sub s. The reason is it is the largest possible value of the magnetization. Think about it. If all of the spins were aligned with the field, if all the dipoles were aligned with the field, then the total magnetization would be n times m divided by v. And so, again, remember the 2 should not be there. But nm over v then represents this saturation magnetization. It's the maximum possible value of the magnetization. And that would tend to happen either at very, very high fields or at very, very low temperatures. So we can make a very useful dimensionless plot of this function. Here's what it is if we solve for m divided by m sub s. And if we let m over m sub s equal to y, and mb over kt equal to x, then we can simply plot y versus x here, and we see that it's got this hyperbolic tangent behavior, which makes sense, because as b gets really, really large, then the tendency is for more and more of the individual dipoles to line up with the applied field, so that this fraction, m over m sub s, would get closer and closer asymptotically to 1. And you can say the same thing about the temperature. If the temperature increases, then we would be moving to the left on this plot, and there would be a less good alignment of these dipoles with the applied field. It turns out that this kind of a plot, a dimensionless plot, is really useful because we can make it simply by plotting y versus hyperbolic tangent of x, and we don't have to worry about the value of the dipole moment or what magnetic field or temperature we're interested in looking at. So we can see the behavior of the curve without having to worry about plugging in for constants or parameters. And we'll be doing that again. Now this expression here, this quite simple expression, is actually in very good agreement with experiment for atomic systems that only have 2 energy states. Now it's true that some atoms have more than 2 possible energy states. It all depends on the spin associated with each of the atomic dipole moments. But for systems where there's only 2, we have actually quite nice agreement when we plot magnetization as a fraction of the maximum magnetization versus the magnetic field in Tesla. here we see for 3 different temperatures, very, very low temperatures, and this is for a sample that has copper ions in it, and so the copper ions are the ones whose individual magnetic dipole moments are getting aligned with the applied field. But we can see quite nicely that as you go to higher and higher temperatures, this curve gets shifted out to the right, and so the approach from zero magnetization to full or complete saturation magnetization happens more slowly with the applied field. And if the temperature were to rise above 0.5 Kelvin, this whole curve would shift to the right. Very, very nice agreement. Now, this is how paramagnetic behavior takes place. And you see that, just going back for a second, you see that as temperature, as field goes to zero, right? If the field is large, then you have this nice alignment. But if you turn the field off, you go back to a magnetization of zero, okay, as we would expect. But that's not what ferromagnetism is. Ferromagnetism says that once you magnetize the sample, even when you turn off the field, some of the magnetization remains. So how does that happen? Well, let's first survey experimental properties of ferromagnetic materials. And remember, again, we talked about this in class, the elemental systems that have ferromagnetic behavior are iron, nickel, cobalt, and then gadolinium at just slightly lower temperatures than room temperature. There's lots and lots of alloys, of course, that have ferromagnetic behavior, but these are the elemental ones. So first, there is this spontaneous magnetization, and all that means is that even when the magnetic field is turned off, you still have a magnetization that remains. It's greater than zero, even when the field's turned off, so that makes them different than paramagnets. And secondly, there's a temperature dependence. So this says that as temperature goes up, the magnetization goes down. And it does so in a way that the magnetization goes to zero very sharply at one particular temperature. Pierre Curie, who was Marie's husband, first discovered this back in the late 1890s, and so that special temperature at which a ferromagnet loses its ferromagnetic behavior is called the Curie temperature. And it's very much like a transition in phase, let's say water going from one phase to another. This is an example of a magnetic phase transition, and the mathematics are quite similar. So here is a plot that shows this fractional magnetization, where we have the magnetization as a function of temperature divided by the maximum magnetization versus a fractional temperature, which is actually the temperature of the system divided by the Curie temperature. And so we see, it's really very interesting that this curve and the data points that cluster around it show a universal behavior of all 3 of the common elemental ferromagnets when we make this sort of dimensionless plot. So these 3 different data sets were all determined for different the 3 different elemental ferromagnets, which of course have different values of their maximum magnetization, and they have different values of this Curie temperature. But if you make this dimensionless plot, you see a universal behavior, which is very, very interesting and gives us some hope that there probably is one single mechanism at work, even though it works slightly differently in all 3 materials. So let's see if we can survey the model that was first developed by a fellow named Pierre Weiss. And this model is what we call a phenomenological model. In other words, we're not going to calculate all of the things in it from first principles. We'll simply be making some assumptions about the behavior of the system and then seeing if the model that arises from them gives us a reasonable mathematical description of the phenomenon of ferromagnetism. And it turns out, we'll see this curve again, but the solid line in this curve comes from the predictions of this Weiss model. So this historically was known as the Weiss molecular field theory, and it dates back to 1907. It was the first of what are called today in theoretical physics mean field theories. These are theories where we make some kind of average or mean field assumption about the field that a particle interacts with. So here's the question that Weiss had to try to answer. How can spontaneous magnetization occur? Weiss assumed, as we did in our model for paramagnetism, that each atom had a permanent magnetic moment, and then he just postulated the existence of some type of inner field that he called a molecular magnetic field inside the ferromagnetic material. He knew somehow that even when we turn off the external field, the dipoles were staying lined up. So he reasoned that there had to be some inner field that was keeping them lined up. Now, the true interactions between the individual dipole moments are not dealt with specifically, but they're simply represented by this inner field. And here's where we recognize that this is a mean field model. This inner field that any individual magnetic dipole experiences is considered to be an average or a mean field of all of the other dipole moments in the solid at the location of the dipole moment that we're focusing on. So we get rid of, from the standpoint of any individual dipole moment, we're not worried about the specific moments around it. We're just saying that there's an average field that they all contribute to that this one dipole experiences. And so we're assuming that all dipoles in this solid behave the same way because they see the same average field. And it seemed reasonable to Weiss, and here's the main assumption that he makes, that the magnitude of this inner field, B sub I, would be proportional to the magnetization of the sample. So remember, B and M have different units, so that's why we have a mu naught in here. But this term lambda is referred to as the molecular field constant. And what you would expect is, for a sample that had a larger magnetization, that must be because the inner field was larger. Right? So the larger the molecular field constant, the stronger the inner field, and the more the ferromagnetic behavior would persist even at high temperatures, the more complete the alignment of these dipoles would be. So this is the main assumption that Weiss makes, so that if we apply an external field B0 to a sample, the net field inside is given by B0 plus this inner field, the molecular field. So it's B0 plus lambda mu naught M. And what we're going to do is use this expression to calculate both the high and the low temperature limits of ferromagnetic behavior. And the way we'll do this is, first of all, to look at this equation and say, all right, if this is the net field when there is an applied field acting on the sample, let's now turn the applied field off, where the B0 would then go to 0. So when the applied field goes to 0, all we have inside is just the second term, which is this inner or molecular field. So what do we do with that? Well, we can take this field and substitute it directly back into the equation for the magnetization that we derived for a paramagnet, right? Because we were then assuming that the magnetization would be related to the external field that was causing the individual dipoles to line up with each other. Well, now there is no external field, there's just the internal field, this inner field. So we just take that, the lambda mu naught M, and plug it in for B in this expression for the magnetization. So we get hyperbolic tangent of M lambda mu naught M over KT. Now look at this equation. This is what's called a transcendental equation, and that's because one of the variables, M, that we're trying to solve for, that we expect to be a function of the temperature, is not only on the left-hand side of the equation, but it's buried in the argument of the hyperbolic tangent function on the right-hand side. So this turns out to be an equation that we cannot analytically solve for M, but we can solve it numerically. In order to see how to do that, first, we're going to split the term and the argument apart, and we're doing this because we're going to make a couple of definitions, but all that really has happened is instead of an M, we have M sub s, M over M sub s. So the M sub s's would cancel, leaving what we started with. But we're doing it this way because now you can see the left-hand side is this fractional magnetization, and now that same term is inside the argument of the hyperbolic tangent function. So let's define, first of all, a parameter that's in this argument that has dimensions of temperature. The first term inside the argument must be dimensionless because the hyperbolic tangent itself is dimensionless. The second term is the ratio of two magnetizations, so it doesn't have any dimensions. So this term here, apart from the T, must have dimensions of temperature. because the whole thing has to be dimensionless. And so what we'll take is everything that's in that expression apart from the T, we will call a temperature, and we'll call it T sub C. It turns out that this is exactly the Curie temperature. So here, let's follow this through. M lambda mu naught M sub S over K. That is this term that has the units of temperature, and then all we have to do is substitute in for M sub S. And that came from our treatment of the paramagnet. We know that that would be where all of the individual moments get lined up with the field. That's the maximum value you can have. So M sub S is little m times n over the volume. And since there was already a factor of little m in there, we end up with little m squared. We call this the Curie temperature. So what this gives, if we make this identification, now let's rewrite the hyperbolic tangent term. We've got hyperbolic tangent of Tc over T times m over m sub s. And this makes things a little bit more tractable. What it suggests we do is pick a value of T for a particular T. If we know what this T sub C happens to be, which depends on all these parameters of the material and of the individual dipole, we can solve for the ratio m over m sub s. And we can plot a curve for that fractional magnetization versus temperature for a ferromagnetic material. Now, we're actually going to do it slightly differently, but we can also get some insight from a graphical technique. All right, so let's just take m over m sub s, and we'll call that y. It's a dimensionless quantity. Then we'll also do the same thing inside the argument. So y is hyperbolic tangent of Tc over T times y. And now let's take everything inside the argument and call it x. So we have y equals hyperbolic tangent of x. Well, you see that if we do that, x is related to y. So we can also use that definition and solve for y in terms of x. We defined y equals m over m sub s, and therefore y is also equal to T over T sub C times x. So what this does is it allows us to find a solution to this transcendental equation for the magnetization by plotting two different graphs on top of each other and looking for solutions. All right, so let's just summarize this here. Here's what we had. We let m over m sub s be y, and then we also let x be equal to everything that's inside this argument here, which was Tc over T times y. So that means we've actually now got two graphs. We've got y equals hyperbolic tangent of x. That's y as a function of x in one form. But then we also have a linear function where y equals T over T sub C times x. And if we plot these two functions on the same graph, an intersection point will represent a solution to the original equation. It's just a useful solution to a graphical type of solution to an equation. So what does that look like? Here are the two functions. We plot y versus x. Well, the hyperbolic tangent function is simple. We've plotted that one before. And now the second one is a linear function, where the slope of the line, we plot y versus x, the slope is this ratio T over T sub C. So at high temperatures, the slope of the y versus x graph will be high. And so let's consider a temperature T1 where it's so high, the only solution, the only crossing point of these two graphs is at the origin, where y and x are both equal to 0. And that's kind of a boring point. That means that at this temperature, at temperatures that high, the magnetization will simply be 0. But notice what happens if we shift to lower temperatures, where the slope of this line gets smaller. If it gets small enough, let's just consider a lower temperature T2, then there will be a crossing point, and that intersection represents a solution. At that temperature, T2, right, then the solution has a particular value of x, which represents a particular value of the magnetization over here on the vertical axis. So this shows spontaneous magnetization, where you would have a magnetization at that temperature where there's no applied field. So the critical temperature, which is the Curie temperature, would be, if we start at temperature T2, remember as we increase the temperature, we're going toward the T1 line, we're making it steeper and steeper, and eventually you would get to a line where you would only have the intersection at the origin. It would be tangent. The linear curve would be tangent to the hyperbolic curve and would intersect only at the origin. So that slope, that special slope, would represent the Curie temperature. So just to summarize, on this graph, as t goes down, which means you're going to the right, you're making your linear curve have a lower slope. As t goes down, the crossing point x goes up, and that means the magnetization is going to get higher. So as t goes down, the magnetization gets higher and approaches the maximum value. By contrast, if t goes up, if you go from t2 toward t1, the crossing point, the solution for x gets smaller, right? Which means the magnetization gets smaller. And eventually, at the critical temperature, the magnetization goes to zero. So this is exactly the kind of phase transition that we were looking for. A numerical solution of this equation, which is easy to do when you do it in dimensionless form, gives the same graph I showed earlier, where you have this fractional magnetization plotted versus this fractional temperature, and you see for all of these three elemental ferromagnets a universal type of behavior. It's really, really remarkable, and shows us that there's something very common happening in all ferromagnets. Notice that this mean field model, which really kind of averaged out any of the individual interactions between magnetic dipoles, it gives really very reasonable agreement with experiment in this graph, except where? Take a look at that graph and see if you can show me where the agreement is not so good. And it turns out it's precisely where you might expect that a model with the mean field approximation would begin to break down. And to go beyond the mean field approximation is the goal of many efforts in statistical physics, especially to do quantitative analyses of very complicated phenomena like phase transitions. So we'll talk about that a little bit more in class, and that's where I will see you.